time. So let's get going. So because today is Wednesday, as promised, we're going to have every Wednesday our Work Habit Wednesday. It's part of the 1 hour per day guarantees. So I'll try to be sort of equal parts positive as well as scolding when I need to be. So the first thing, the positive thing is you guys are still coming to class. It's day 2, so you don't get a gold star yet, but that's good to see that you're all still here, because the room will, in most cases, be a lot less full than this in a few weeks, but hopefully we keep that up. Now, the one thing I want to remind you about is, as part of today's weekly reminder, is there is a review assignment in Blackboard. One thing I want to be clear about, because I don't think I mentioned this in class last time, the review assignment is actually in the exams folder in Blackboard. It's not in the homework folder. So if you had trouble finding it, it's in the I don't know why they put it in the exam folder. I didn't put it there, but anyway, it's in the exam folder, so you'll access it through there, but it's still through Blackboard in the same format as all the homework assignments will be. I want to remind you that that's there, and hopefully if you've found it, you've already at least done an attempt on it. And if there are problems you don't understand or had trouble with, make sure you get help from me. So that's something you want to get on right away, because we're getting into the first chapter stuff already. We started it last time. We're going to plow through more of it today, and so you don't really want to procrastinate on this review chapter. If there's anything in there you have any confusion about, try to get that addressed right away. So that's kind of my reminder for today is about that, and that's something that you should already be in the process of doing or doing as soon as possible if you haven't yet. All right, so that's let's move into the class material then. So if you'll recall, last time we introduced the first 2 of our 3 mass laws. So these are kind of some of the earliest principles of chemistry that were revealed. And that led to some, as we'll see today, some very important ideas about how matter is composed and the fundamental particles that make up matter. The third one we want to talk about today, to wrap this up, is the law of multiple proportions. This one is the most confusing to put into words. So of the 3 mass laws, it's the one that students certainly have the most trouble wrapping their heads around, and that's understandable. I'll give you sort of a definition of it first, which is initially not going to make a lot of sense, but I'll try to break it down in as simple terms as possible. So what we're talking about in the law of multiple proportions, and the name kind of gives this away, is we're talking about 2 or more compounds now. So we saw that the law of definite composition that we finished with last time says for a given compound it's going to have a certain composition of elements in terms of their mass ratios or mass percentages. Now we're talking about, for the law of multiple proportions, 2 or more compounds that are made up of the same elements, okay? So if we have 1 gram of element A combines with element X to form 1 compound. So remember, what the law of definite compositions tells us is that this compound is going to have a well-defined specific ratio of A to X in terms of masses. But what's sometimes possible is that 2 elements can combine to form 2 different compounds. All right. Now, we should be familiar with this in our everyday life, because we talked about carbon dioxide last time, which is the air that you exhale from respiration, and then there's also carbon monoxide, which is one that you want to avoid because it's poisonous and it can sometimes cause problems in homes. And those are both 2 different compounds that have carbon and oxygen in them. So here's the situation we're talking about with the law of multiple proportions: same 2 elements but forming 2 different compounds. Now, when this happens, in order to form 2 different compounds, the mass ratios have to be different. And if we compare those mass ratios, the masses of element X that combine with 1 gram of A are small whole number ratios of each other. And when we mean small whole number ratios, we mean like 2 to 1, 3 to 1, 3 to 2, and so on. All right? So as an example, let's say we have 1 gram of element A, and it combines with 2 grams of element X to form some compound. All right? If we take 1 gram of element A and combine it with element X to make a different compound, the amount of X that we're going to combine is going to be something like 3 grams or 4 grams or, something that's a simple relative of those. So that's what law of multiple proportions tells us, is that if we're using the same two elements to form two different compounds, the ways that they combine are very closely related to each other by small whole numbers. All right. So here's an example of law of multiple proportions. I'm just putting numbers onto it. Helps make things a little bit clearer. So here are two compounds that contain only iron and oxygen. One of them you've heard of, which is rust. It has a more formal name than that, but then another one that I'm showing here, which is clearly different than rust because it's black, it has totally different properties otherwise, is called ferrous oxide. Now they both only have iron and oxygen in them, so this is a situation where the law of multiple proportions should apply because it's two different compounds but the same elements in each compound. All right, so if we look at ferrous oxide, what we're going to figure out is what's the sort of mass ratio of the two elements. So we can do this in either order. We can do oxygen over iron or iron over oxygen. Doesn't really matter. We're just comparing these two. So we're going to do this ratio here, which is basically going to tell us sort of that first statement of the law of multiple proportions. How many grams of oxygen combines with 1 gram of iron to make this compound? By dividing the two, we're basically normalizing or making a ratio with the mass of iron in the denominator. But as I said, we could do it in either direction. It would work. So we see from the mass percentages here that we have 22.7% oxygen in, we're doing ferrous oxide, so the mass percentage of oxygen is 22.27. So that means out of 100 grams, we have 22.27 grams of oxygen and 77.73 grams of iron. So that's the mass ratio of oxygen to iron using the percentages as masses, assuming we have 100 grams of the compound. So when we divide this, we get a ratio of 0.2865, which another way of thinking about this ratio, as I said, is if we're making ferrous oxide, the black compound over here, if we use 1 gram of iron, we would use 0.2865 grams of oxygen. All right? Now, what the law of multiple proportions tells us is that if we combine iron and oxygen in different ratios to make a new compound, in this case rust, then the ratio that we get for rust should be a very simple multiple of 0.2865. It should be maybe 2 times this, or 1.5 times this number, or maybe 3 times this number. But it's not going to be just any random number, or not going to be a huge multiple of this. It's going to be a relatively small whole number ratio of this. So if we compare those then, if we do the same calculation for rust, where I take the mass ratio in the same exact way, oxygen over iron, in this case, for rust, the percentage of oxygen is 30.06, which means in 100 grams of the compound, we'd have 30.06 grams of oxygen. The rest, 69.94 grams being iron in that compound. When we divide those, we get 0.4329. Now, it's not obvious by looking at the numbers that these are simple relatives of each other because they're decimal numbers with 4 places. But if we divide the two, we should get a simple ratio. So if we take, again, in either order, it doesn't really matter how we do this, 0.4329 divided by 0.2865, that ratio is exactly 1.500, or written as a simple whole number fraction or ratio, 3 over 2. All right, and that's kind of what law of multiple proportions tells us, is that, again, if we make ferrous oxide, which has this specific ratio, the ratio we would get for a different compound should be a simple multiple of the original ratio. Now, again, that's it's kind of a word salad and sort of hard to conceptually grasp right off the bat. The point is, when we're doing homework questions and exam questions on these different mass laws, usually they're going to be more conceptual in nature. We're going to ask you, which mass law is demonstrated by the following situation or the following statement. And the dead giveaway for the law of multiple proportions is that it's the only mass law that deals with 2 different compounds. So if you're presented a situation that involves something about 2 different compounds, you should immediately think of law of multiple proportions. It's the only one that deals with more than one compound at a time. And additionally, law of multiple proportions, as we said, the other key point is that the 2 compounds have to have the same elements in them. So if that's your situation and we're telling you anything related to that, you should automatically know that, okay, we're talking about law of multiple proportions here. And again, some of the finer details might be hard to grasp, but it is the more complex mass law, but I think not too difficult to understand in the context of this course. So let's now review the 3 that we have. 2 of them we introduced last time. So This is probably the simplest of the three is the law of conservation of mass, which we're probably already familiar with from before in our other courses we've taken, which is that mass or matter is neither created nor destroyed during a chemical reaction. All right, so the mass that you start with in a chemical reaction is going to be equal to the mass that you produce as the result of the reaction. And then the second one we introduced last time was the law of definite composition. This also deals with compounds, but it's going to be dealing with a single compound in this case. And what it says is that each chemical substance, I guess if we want to be more general, we can say substance, but it would be either elements or compounds in this context. Each pure substance has a specific proportion of elements by mass. And so that's sort of what distinguishes one compound from another, is the mass proportions of the elements. And we learn how to then calculate and use the mass percent in different contexts to relate amounts of elements in a specific compound. And then the one that we just finished introducing, which I'll put into slightly different words here, is that if two elements combine to form two different compounds, what's going to make those two compounds different from each other is that they have different mass ratios. So they might have the same two elements, but the ratios of the two elements are going to be different if they're making different compounds. This is not entirely rigorously true, but for this point in the course, it's fine to think of it that way. So if two elements combine to form multiple compounds, more than one compound, each compound will have a distinct mass ratio. So basically that's what's going to distinguish the compounds from each other, is the mass ratio of the elements, even though the elements themselves that are in there are going to be the same, but they're going to be in different ratios. So each of the compounds that forms will have a different mass ratio for the two elements. All right, and we saw that just in the example we looked at now with ferrous oxide and rust. You'd find the same thing if you compared carbon monoxide to carbon dioxide. Same two elements, but different ratios in the two compounds. But then, law of multiple proportions takes it a little bit step further, and this is the part that's a little bit hard to always necessarily wrap your head around right away. But if we look at the ratio of these two ratios, so we're talking about a ratio of ratios here, which is potentially confusing to think about, but we're taking two mass ratios, and then we're taking the ratio of those ratios. That would be a small whole number or simple fraction. All right, so those are the three mass laws, and again, these are some of the earliest chemical principles that were revealed by careful studies of chemical compounds, applying the scientific method, making observations as we introduced. Now, the other thing we talked about with the scientific method is that repeated application of the scientific method will give you laws which are sort of consistent, always observable statements, either in qualitative or mathematical form, and these are the first three laws in this class we're talking about. And then when you have laws, you also then would want to come up with a theory to explain those laws. So the law, again, is what we observe, and these are three things we observe about chemical substances, about chemical reactions, chemical substances. Those are the three observations, the three laws that came out of these studies. And then what's also then important is to come up with a theory that explains, why are these laws even exist in the first place. And so the theory, which is the explanation for these laws, is credited to a scientist named Dalton, and it's called Dalton's atomic theory. And so basically, it's useful for you to think about this. So as you spend 1 hour per day on this course, you can spend a part of that time this week really sort of trying to internalize the relationship between these three laws and then this theory that I'm going to give you, and sort of think about how does this theory explain the law, which I'll give you some examples of, but it's helpful to think about it in your own terms as well. So the Dalton's atomic theory can be broken down into a few different parts depending on how you divide it up. There's no set number here, but I have sort of 4 statements that are part of this theory. And so the first is that substances are composed of tiny particles called atoms. All right, so it's called the atomic theory, and of course then the first part of it is that substances are composed of atoms. All right, now we said that the ancient Greeks were the first to even come up with the idea of atoms, but they had no real scientific basis for that. They just sort of proposed them as existing. But these 3 laws and the many experiments that were done to formulate these laws sort of are consistent with the idea that substances are composed of atoms which cannot be decomposed further. All right, and so that basically means the atom is the simplest particle that makes up all matter, and you can't break it down any further than a single atom. All right, and then another part of this, which is related, is that atoms cannot be converted into different atoms. So during a chemical reaction, you can't convert one atom into a different atom. Which is to say that elements cannot be interconverted. So if you're doing a chemical reaction that involves, let's say, the element carbon, you can't turn that carbon into oxygen using a chemical reaction. Or all the atoms that are carbon are going to still be carbon at the end of the reaction, maybe just combine with other elements to make different substances. But that's sort of part of the law of conservation of mass, which is that, again, matter is neither created nor destroyed, and the reason is that the atoms that make up that matter cannot be destroyed or cannot be converted into something different. They start out as one type of atom, and that's what they're going to stay as throughout the chemical reaction. All right. And then if we look at how are atoms of an element distinct from each other, so what makes the different elements different? So each element is made up of atoms, but why are the elements then different from each other? Atoms of a given element have the same mass and other key properties, which we'll get into. And they're all distinct from other elements. Now this is the one that we'll learn a little bit later on is not entirely true, but it was a good starting point for sure to sort of understand how are the different elements different from each other. Why are carbon and oxygen so different? And at sort of the atomic level, the proposal was that carbon atoms have a different mass than oxygen atoms, and then all carbon atoms have the same mass, all oxygen atoms have the same mass, all atoms of a given element have the same mass as each other. That's not entirely true, but it was sort of the starting point, and it had to be refined a little bit. So we talked a little bit about, theories are not always set in stone. As we do, as we learn more things, we often have to refine the theory. So Dalton's atomic theory is not perfect, and this is the one part of it that, as we'll see, needs to be refined a little bit, but it is certainly a good explanation for all these mass laws. And then finally, talking about chemical compounds, and then relating this then to those last two mass laws about chemical compounds, they're going to be formed when atoms of different elements combine in a specific ratio. So again, this takes it down to the atomic level. People knew that elements combine to form compounds, and then what's happening at the microscopic level is that the atoms that make up those elements are combining in specific ratios. And basically, any chemical reaction is going to involve what we call reorganization of atoms. So as I've said, it doesn't change atoms into different types of atoms. It doesn't create or destroy atoms. It just reorganizes them and pairs them in different ways with different elements. And this is key. This last one here is key for both the law of definite composition and the law of multiple proportions, because if you're combining atoms in a very set ratio to make a compound, then the masses of those elements in the compound would also be fixed in that ratio. And then similarly, for law of multiple proportions, if you're combining things with simple whole number ratios of atoms, so like carbon monoxide is 1 carbon, 1 oxygen, and then if you're going to make another compound that has carbon and oxygen in it, you would combine carbon with maybe 2 atoms of oxygen, but in simple ratios, which then translates to the mass ratios also being close related to each other in simple ways. So these all sort of relate to each other, and these are kind of the initial ideas that led to the sort of the proposition of atoms in being sort of the fundamental substance. Now, another concept that I want to introduce now, it seems a little bit out of place, but it's in our book, so I want to make sure we touch on it a little bit. And another important part of early chemistry. So, so far we've learned from the mass laws and Dalton's atomic theory that, atoms combine in specific ratios to form compounds. You know, they combine at the atomic level, and then those mass ratios can be determined and talked about as well. But then the question is, you know, how do we know what that ratio is? How do we know that carbon monoxide is 1 carbon and 1 oxygen, and that carbon dioxide is 1 carbon and 2 oxygens? How is that figured out? We're going to just give the real sort of you know, broad picture of that for now, which was sort of, these are the two people, Guy Lussac and Avogadro, that were sort of key for determining chemical formulas for the first time, so actually knowing what are the ratio of atoms in a compound. So what Guy Lussac observed was that, and they were doing studies on gases, and they were reacting different gases with each other to make new gases, basically doing chemical reactions in the gas phase. And so at the same at equal temperature and pressure, now we're going to have a whole chapter on gases later, so we're going to, as I said, just give the real simple definitions now, and some of the details are going to be foggy at the moment, but that's okay. That's kind of how general chemistry goes. We sort of gradually build up the complexity. So at equal temperature and pressure, gases combine in chemical reactions in fixed whole number ratios. All right, so he was studying reactions involving gases, and what he found then was that they always combine in very simple ratios with each other. Okay. So for example, if he reacts hydrogen and oxygen, which is a very violent reaction, it would be cause an explosion, but the reaction that happens is hydrogen plus oxygen react to make water. As we know, water is the formula H2O. And what Guy Lussac found was that if he takes 2 volumes of hydrogen, so let's say 2 liters or 2 whatever of hydrogen, 2 volume, and then that would always react with 1 volume of oxygen. So they would always react in that ratio, and they would then form 2 volumes of water vapor, which is just gas phase water. Again, it involves a lot of heat, so it's going to all be in the gas phase initially at least. So when you combine hydrogen and oxygen to make water, as one example, they always combine in this 2-to-1 ratio, provided the gases are at the same temperature and pressure, and that's what you always see as a result of this. And then the way that Avogadro interpreted this, which we're going to, again, learn more about later on in the course, is that if you're at the same temperature and pressure, which Guy Lussac was for his experiments, equal volumes of different gases have the same number of particles. I guess we'll say atoms at this point. This is an oversimplification, but I guess you could say atoms or molecules. It depends on what that gas is made up of. Is the gas just made up of atoms, or is the gas made up of molecules that are in the gas phase? But it works either way. So basically, if you have 2 totally different gases, let's say hydrogen and oxygen, like the 2 we talked about before, but they're at the same temperature and the same pressure, if you have the same volume of each of those gases, they will also have the same number of atoms in them. And so then what that leads to is, if Avogadro is correct, which he was, what that means is that this equation up here, 2 volumes of hydrogen plus 1 volume of oxygen makes 2 volumes of water. What it means then is that if we combine 2 molecules of hydrogen, so now if we go down to the microscopic level and talk about the atoms and molecules, hydrogen exists as molecules, which we don't need to worry about too much for now. But if we combine 2 molecules of hydrogen with 1 molecule of oxygen, same 2-to-1 ratio at the atomic level forms 2 molecules of water. And so the whole point of all of this is that by studying gas phase reactions, and then by looking carefully at the ratios that the gases react with each other, they could then figure out what is the ratio of the elements in the product that formed. And so they figured out from this that water contains 2 hydrogens for every 1 oxygen. And as we now know, and you probably already knew, the formula for water is H2O. So it was these experiments, really the key takeaway message is that it was these experiments that allowed chemists for the first time to actually determine the specific chemical formulas of certain substances. Not all substances, but for ones that react in the gas phase, they were able to do that. So we kind of, again, look at this in more of a pictorial sense. If you look at I have a note here. Most gaseous elements are diatomic, so they exist as molecules with 2 hydrogens H2, 2 oxygens O2. Not something you need to worry about now, but will come up later in the course. And so what that basically means is if we sort of blend these two ideas together from Gay-Lussac and Avogadro, Gay-Lussac noted that, as we just said, 2 volumes of hydrogen combines with 1 volume of oxygen to make 2 volumes of water. So this was sort of the chemical reaction he was studying, and he just measured, again, the volumes of each gas that were involved in these reactions and the volume of product that formed. And so what you then use Avogadro's interpretation to show you is that means that the molecules are combining in the same ratio. So hydrogen, as we said, is H2. They didn't necessarily know that at the time, but we know that now, so we'll try to be accurate. So if you have 2 volumes of H2, that's the same as saying if we had 2 molecules of H2, if we go down to the microscopic level, 2 molecules of H2 will react with 1 molecule of O2, and they will form, let me do this in a different color to be consistent. So these are both oxygen. So two molecules of H2, 1 molecule of O2, and then the product they form, water, because it has two volume equivalents being formed, is going to have also 2 molecules being formed. So you're going to have oxygen and then bound each 2 hydrogens. And so in this sort of deductive way, they were able to figure out that the formula of water is H2O because hydrogen and oxygen combine in a 2-to-1 ratio and then make 2 molecules of water, which must then have a ratio of 2 hydrogens to 1 oxygen. Okay, so that's how I figured out. But then it doesn't always work the same for all gases. So if we react hydrogen instead with chlorine, in this case, if you take 1 volume of hydrogen, get a different color here. It's not going to let me change colors today. Come on, guys. Come on, tablet. We can do it. There we go. All right. So if we have 1 volume of hydrogen, this will now combine with only 1 volume of chlorine. Cl2 is the symbol for chlorine. And then the product would be 2 volumes of hydrogen chloride. And so with this data in mind and with the interpretation that Avogadro provided, you could formulate then that HCl has the formula 1 hydrogen and 1 chlorine. So each molecule of HCl is 1 of each. Because again, that's the ratio they combined in, and that's the ratio of the product that formed. And that's the only way for that to make sense. Because again, you can't create or destroy atoms. So if we're starting with a total of 2 atoms of hydrogen on the reactant side that we're mixing together with 2 atoms of chlorine, what we form is going to also have a total of 2 atoms of hydrogen and 2 atoms of chlorine, and they must be in a 1-to-1 ratio for the volume ratios to work out. So again, this is a little bit early to fully understand that, but we just want to introduce that as the idea of these are the types of experiments that early chemists did to figure out chemical formulas. And then, of course, from there, the field developed even more and more to be able to start figuring out chemical formulas of many other types of substances in a lot of different ways. So we're going to leave that for now. What we're going to move into is, having now introduced the idea that substances are made up of atoms, basically elements being made up of one type of atom, compounds being made up of combinations of different atoms, we want to start talking now about some of the experiments that were done to actually understand what does the structure of an individual atom look like. So, is an atom just a random blob of matter, or does it have actually some sort of subcomponents to it? Does it have a structure to it, and so on? And that's really what the major part of this chapter, and then even moving into chapter 2, is going to really look at, is the sort of developing ideas of how to understand the structure of the atom and what makes up an atom and all the different properties that then result from it. So the first thing we'll talk about is what's called the cathode ray experiment. So this is J.J. Thomson is the gentleman who's credited with this discovery. So I'll show the pictures of a lot of these scientists. They all look very unhappy, which always was weird to me because they made some of the most important discoveries in human history, and they're not very pleased about that for some reason. But he's not the most unpleasant that we'll see today. But anyway, he was the one that is credited with this sort of discovery, and he did an experiment called a cathode ray experiment. So essentially what you do is you take a piece of metal, you apply a very strong electric current to it, and then it generates a beam which was known as a cathode ray. And then what you can find is that by using an electric field, you can bend that electron beam. So this blue line here is that electron beam. It's formed over here at what's called the cathode. That's why it's called a cathode ray experiment. So you put a huge electric current into the metal, and then you generate this beam, which you can detect using what's called a phosphorescent screen, similar to the very old TV technology that nobody uses anymore. But if you remember the old cathode ray TVs, the ones that sat on the floor and weighed about 800 pounds, those are cathode ray TVs. They use the same technology to generate pictures. But the whole point of this experiment was that he noticed that in the presence of an electric field, which is shown here, the beam sort of bends, okay? So let's go over the key observations one by one. So these cathode rays, as they're called, are repelled by the negative pole of this microphone's a little bit hot. Let me turn it down. All right, hopefully that's better. So the cathode rays are repelled by the negative pole of an electric field. Now, something we expected you to know before you started this course is that charges that are the same repel each other. So then what that logically conclude from that is that the cathode rays are negatively charged. So they're repelled by the negative side of the electric field. That means they're also negatively charged, okay? So he called these electrons. So he sort of came up with this terminology, electrons. And what he also noticed is that they could be produced by a lot of different materials. So it's not just that, one special metal that he was using as the cathode produced electrons. Basically everything he tried, at least every metal, which are the types of substances that work in this experiment, they all produce these cathode rays that are all negatively charged. And so then what that led him to conclude was that all atoms, because all these different materials he was trying as cathodes, and they now know are made up of atoms, that means all atoms must have electrons, okay? Because everything he tried seemed to generate these cathode rays, these beams of electrons. And so that must mean that all atoms have electrons associated with them. And that's certainly true. We now know today that's definitely true. And the other thing that this experiment did was it got a little bit quantitative, but not perfectly quantitative. So, asking the question, well, how big is an electron, or how much charge does an electron have? This experiment by itself is not enough to do that. We'll talk about the next one, how they got these numbers, but it was enough to determine the charge to mass ratio. So by varying the electric field and by measuring how much the electron beam bends in that electric field and then doing some physics calculations that I won't go through, you can determine the ratio of mass and charge, or charge and mass, in an electron. But you can't determine those two numbers exactly. What is the charge, what is the mass? You can just get the ratio between the two. But he figured that out. So this was sort of credited as the discovery of the electron. So J.J. Thomson knew that, figured out that all materials have electrons in them, have negatively charged particles. And then a further experiment done on the electron. This guy looks even more displeased with the result, but he shouldn't be. This was Robert Millikan. I think the real reason is that back then it took like an uncomfortably long amount of time to get your photograph taken, so it was like too difficult to smile for that long, and they just had a really serious face. But anyway, he doesn't look happy. But he came up with this very clever experiment, the oil drop experiment. All right, so what he did in this one was he used what's called sort of what do they call these? An atomizer, or a kind of like an aerosol type spray thing to make really small drops of oil. And then he used electric field or electric charge to basically charge these oil drops, so to make negatively charged oil drops. So again, we're not getting into the technical details of how he did this. He made negatively charged drops of oil, very small drops of oil that had negative charge on them. So again, they had electrons associated with them. And then he used down here an electric field. So the electrons went through the positive plate of the electric field, and then by gravity were carried down towards the negative plate. But then if you turn up the electric field high enough, remember that the like charges are going to repel each other. So you have this negatively charged plate on the bottom of your electric field. The oil drops are falling towards that, but then they're going to be repelled by the electric field, and eventually they're going to hold and suspend without moving at all. So if you've taken physics classes, you probably learned about, like free body diagrams, or basically net force equals zero kind of things. And that's exactly what's going on here. They set up an electric field that was just the right strength to stop these oil drops from falling. They knew the masses of the oil drops, and through again some math that we're not going to go through, they were able to figure out the mass and the charge of the electron. So let's go through that again one by one. So they had falling negatively charged oil drops. So that's what they're studying. And they turned up the electric field to stop these drops from falling, basically to perfectly balance the force of gravity with the electric force between the electric field and the electrons in the oil drop, okay? And so then what he found is he was able to measure the charge on each oil drop, and he found that these charges occur in very regular whole number intervals. So what that means is if one oil drop has a charge of 1 in some unit, another oil drop could have a charge of 2, 3, or 4, but it couldn't have a charge of 1.27 or 37.36. So basically the charges occurred in very regular ratios, which told him that there are sort of discrete particles. These electrons are discrete particles that are responsible for that negative charge. And you can't have half of an electron or a third of an electron. You can have 1 electron or 2 electrons or 3 electrons, some whole number of electrons that's responsible for that charge, but you can't just have any continuous value of charge that you want, okay? And he was also then able to determine from this the mass and charge of an electron. Now, what was later found out, I don't think I think I have this number later on, but I'll give it to you here. The charge of an electron it's negative, so that's what the negative sign means. Negative 1.60 times 10 to the minus 19 coulombs. Coulombs is the SI unit for charge. We're not going to use it much in this course, but that's the value. It's a very small value of charge for a single electron, but it can be measured, and this is what this experiment determined. And again, the other key implication of this is that when he measured the charge on these oil drops, if the oil drop had 1 electron, this would be the charge on the oil drop. Then the possible other charges you could see would be some whole number multiple of this. So you could have an oil drop that had a charge of minus 3.2 times 10 to the minus 19, which would be 2 electrons. Or you could have an oil drop that had a charge of minus 4.8 times 10 to the minus 19, which would be 3 electrons. But you can't have any other numbers in between those. They occur in those regular discrete intervals of 1.6 times 10 to the minus 19 coulombs for each individual electron that you can have. So he determined again that electrons are discrete particles, and then they have a specific mass and charge that he was able to measure. So from these two experiments, it was actually Thomson that came up with this. The first model of the atom is called the plum pudding model. So plum pudding is a dessert that's popular in the UK, which likely means it doesn't taste very good, but it looks like this down here. Apologies to anybody in here who's of English descent. But anyway, basically the plum pudding model states that, so if you have electrons, we now know that atoms have electrons. They must also have some sort of positive charge in them because atoms don't have a net charge. Atoms themselves are charge neutral. They have 0 charge as a whole atom. So if they have a negatively charged electrons in them, they must also have positive charge to balance that. And so the proposal for the plum pudding model was that you have these discrete negatively charged electrons, which are shown in these yellow particles here, and that the positive charge was just sort of amorphous continuous blob. Okay, so that was what's called the plum pudding model, where basically the bread that makes up the pudding is the positive charge, and the little raisins that are, or plums that are in there, are the electrons sort of floating around in that. So that kind of just proposed that there's a blob of positive charge and the electrons are just randomly floating around in there. Okay, so that was the plum pudding model, which is that atoms consist, they have electrons, we now know that. We now know the electrons are discrete particles, and those electrons are going to be held in place by a diffuse cloud of positive charge. All right, so this initial model did not propose that there was discrete particles that made up the positive charge. They just said, okay, there's a blob of positive charge and the electrons are floating around in that. A pretty simple model, and at least consistent with the idea of that were known at the time. And the electrons are basically randomly embedded in this positive charge. So there's no real regular structure to it. They're just sort of randomly floating around in there. All right, so that was his proposal, a model. This is called the plum pudding model. Model is kind of like a theory, I guess, in some sense. It's a proposed explanation for things based on what knowledge is currently known. And it turns out it was dead wrong. So this is, again, a good explanation, a good example of the scientific method where, with the available information they had, they proposed something and they did more experiments to test it. And it was found to be wrong. And the key experiment that proved this to be wrong is called the gold foil experiment. And this was done by Ernest Rutherford. I don't have an unhappy picture of him, but presumably he was, and it also has a permanent scowl. But this is the experiment that he did to basically test the plum pudding model. So skepticism is an important part of the scientific method. So Rutherford didn't just say, yeah, okay, plum pudding model sounds good. Let's pack up and go home. He actually wanted to test whether or not that model is reasonable. And the experiment he came up with to test this was he had what's called an alpha particle emitter. So alpha particles are very dense particles that they move really fast too. So basically, think of it that, and then he had a thin foil of gold foil. So he had these alpha particles, very dense particles that he was shooting at a very high velocity, and he was shooting them at a very thin piece of gold, a gold foil that was, really, really thin. And this is kind of like, and what he thought was going to happen is that this is basically like shooting a BB gun at a piece of paper. So these alpha particles are these really fast, dense particles. They're going to fly towards the gold foil, and they're just going to charge right through it, kind of like shooting a BB gun at a piece of paper. And that's what he thought would happen. So if the plum pudding model is correct, the mass in the atom is very diffuse, they're not very dense, and basically that means if you shoot something that's really dense and really high speed at it, it's just going to plow right through it. Okay, so that's what he thought would happen. That was sort of the hypothesis, if you will. So what he thought was that the alpha particles would mostly pass through or maybe they would, be slightly deflected. Maybe there'd be some, small collision between the alpha particle and the atoms, and then, the alpha particles would veer ever so slightly. But basically, they're going to just plow right through this piece of gold foil because the plum pudding model supposes that the mass in the atom is very diffuse and that things could just go right through them because they're not very dense. But what actually happened, and this is where it's important to be, very careful when you do experiments and not to have any sort of bias, is that it certainly is true that most of the particles went straight through. So those behaved as expected. They passed straight through. So again, he has without getting into the technical details, a way of detecting these alpha particles as they pass through to the other side. And the vast majority of them went straight through to the other side. No change in their path. But what he found was that some of them were deflected at very steep angles. Or some of them reflected completely back to the source. right? So most of the particles passed straight through, but some of them diverted, got deflected in a big way, or some of them actually bounced straight back to where they came from. And this was not expected from the plum pudding model. So the explanation they came up with was that, and I guess another key point that I didn't mention is that alpha particles are positively charged. So if they collide with something that's positively charged, they should be repelled by it, and that would cause them to deflect as well. But the explanation then was that in order for this to be true, in order for some of these alpha particles to be completely reflected or deflected at very large angles, what must be true about the atom is that the positive charge and most of the mass for the atom they're in a very small area called the nucleus. Now, there's more details we still need to reveal, and that's what we're going to spend the next few weeks in this course doing, but this is largely the correct picture of the atom. You have a very dense nucleus, very small area in the atom that has all of the positive charge in it, and then the electrons are then sort of floating around that, okay? So this is the picture then in contrast to the plum pudding model, which has a random blob of positive charge with the electrons floating around. The new nuclear model of the atom has a very tiny nucleus at the center, shown in that little red and yellow thing, and then you have a very diffuse electron cloud around it. All right, and we have a lot more to talk about with how these electrons are arranged, but for now, just think of it as the electrons are floating around the nucleus, and they occupy a very large space compared to the nucleus. So compared to the size of a whole atom, the nucleus is extremely tiny. And another way then of sort of stating the results of this experiment is that atoms are mostly empty space. Tiny, dense nucleus at the center, electrons floating around in a huge volume outside of that, with, at any given time, most of that space completely empty, okay? And that was the result of the gold foil experiment, which gave us a much more accurate picture of the structure of the atom. Now, there's one other detail that this didn't reveal, and we're not going to go through how this was determined, but there actually is, so we now know that there are electrons, which are the negatively charged particles in atoms. What they call the positively charged particles are protons, and then there's a third one, neutrons. And if you want to learn about how neutrons were discovered, you probably have to take a modern physics course, which was the worst class I ever took, so I wouldn't recommend it if you have to. But anyway, there's now three subatomic particles that we have to consider. Electrons, which were discovered by the cathode ray experiment and further characterized by the oil drop experiment. Protons, their existence was confirmed by the gold foil experiment, and the idea that they're very massive and located at the center of the atom. And then much later on, they figured out, there's also these neutrons that make up some of the nucleus as well. All right, so then let's talk about those three subatomic particles as they're now called. All right, so the nucleus is now known to contain protons and electrons. All right. So it is true that all of the positive charge is at the nucleus, but there are another type of particle called neutrons that are there as well, okay? All right, so the nucleus has both the protons and the neutrons in it. Protons, as we just talked about, have a relative charge of +1. The absolute charge in the SI unit of coulombs is 1.60 times 10 to the minus 19. As I said, that's the charge of the electron, which is the negative of that. The charge of the proton is just the positive number, equal and opposite. The relative mass. So the mass unit that we're going to start talking about a little bit is called AMU, atomic mass units. And what that does is it sets the mass of the proton at 1, okay? Or very close to 1, I should say, okay? So the mass of a proton in AMU scale is about 1. In grams, it's tiny. 1.67 times 10 to the minus 24th. Now, of course, we don't want you to memorize these numbers necessarily, but we want you to understand sort of the differences between protons, neutrons, and electrons in a relative sense. That's going to be important for us to internalize. Now, if we go to neutrons, which are the other particle that are in the nucleus, These don't have any charge. So the neutron meaning neutral is where that comes from. They have no net charge. So they have zero charge associated with them. So that's both the relative and absolute charge is zero. But their mass is about the same as a proton. So the mass that's in the nucleus, which is the vast majority of the mass for the atom, includes the masses of the protons and the neutrons. It's not just one or the other. Okay? And it's the masses of neutrons and protons are not exactly the same, but to 3 significant digits they are. So if you look at the mass in grams of a neutron, if we round it to 3 significant figures, it's exactly the same as a proton. So there's, if you go further and further out, more and more precise, you'll see slight differences, but by and large they're the same as each other. Okay? So you have protons and neutrons in the nucleus, same mass, but protons positive charge, neutrons are neutral. And then the electrons, which we actually talked about first in today's discussion, they have a relative charge of -1. So they're negative. They're exactly the same magnitude of charge as a proton, but opposite in sign, which means that their absolute charge, as we said, is the same number, but with a minus sign in front of it. So one proton and one electron completely cancel each other out in terms of charge. They're exactly the same charge, but just opposite in sign. The difference, though, with electrons is that their mass is tiny. So the relative mass in AMUs of an electron is 0.000549. So it's about 1,800 times smaller than the mass of a proton or a neutron. And in grams, this comes out to 9.11 times 10 to the minus 28. And again, to reiterate, because we don't want you to memorize the exact numbers, but what's helpful to at least have a concept of is that these are about 1,800 times smaller than the protons and neutrons. So that means in a typical atom, as we start learning about how many of each of these particles are in there, at least 99.9% or maybe 99.95% of the atom's mass is in the nucleus. So when we're talking about the mass of an atom, we basically ignore the electrons. They're very, very tiny. They don't significantly impact the mass at all. Just about all the mass for the entire atom is in the nucleus, in the protons and the neutrons. Okay? So that's kind of some important things about those 3 types of subatomic particles. And then what this leads to then is understanding subatomic particles and talking about then how many of each of them there are in an atom is going to allow us to distinguish one element from another. So as we said, all elements are made up of atoms, but the atoms are different from each other. Now what the Dalton's atomic theory talked about that we introduced earlier is that the difference between different elements is that their atoms have different masses. And that's kind of true, but that doesn't really tell the clearest story. So what really distinguishes one element from another is the number of protons in the nucleus. All right? So that's going to determine whether the atom belongs to one element or another, is how many protons it has in the nucleus. All right? And if, as we'll sort of talk about in this course, the very smallest atom, hydrogen, has 1 proton in the nucleus, and the very largest atoms that have been discovered recently artificially have like 118 protons in the nucleus. So there's all these different numbers of protons in the nucleus, and that's going to distinguish one element from another. And then now there are some other things then that are important to consider about what's called an atomic symbol. So when we characterize an atom of an element, there's sort of 3 things we're going to put into the symbol. So there's going to be, I'll put them in 3 different colors so that we can keep them straight from each other. All right, so that's what an atomic symbol is going to look like. It's going to have, the central part is going to be, I'll abbreviate it as X, and then it's going to have 2 terms A and Z associated with it. And this is going to tell us everything we need to know about a specific atom, okay? So X is the atomic symbol, which is basically a 1 or 2 letter abbreviation for the element. So this tells us what element we have. We'll talk about the periodic table a lot more later, but these are the symbols that are on the periodic table. And we always capitalize the first letter, not the second letter. So that part of the atomic symbol just tells you the name of the element, helps you identify what the element is. The other 2 parameters, A and Z, are going to be, these are going to be numbers that are associated with the atomic symbol. So Z is referred to as the atomic number. Sorry, I'll draw Z better. And this is just the number of protons in the nucleus. All right. And then the last one, A, which is shown as a superscript, is what's called the mass number. And this is going to be the sum, the number of protons. I'll abbreviate protons as P plus, protons with a positive charge, and the number of protons plus the number of neutrons, so the sum of those two numbers, neutrons being abbreviated with N0 for neutron, and with zero charge. So the sum of the number of protons plus the number of neutrons is what we call the mass number. So that tells you the total number of particles in the nucleus, total number of protons plus neutrons in the nucleus of that atom. Okay? So those are the three parts of an atomic symbol, and that tells us everything we want to know about an atom. Now the part that Dalton got wrong in his atomic theory was he said that all atoms of a given element have the same mass, and this is not exclusively true. Okay? So that's where we have to introduce the concept of isotopes. So remember that the mass of the element is determined by the number of protons and the number of neutrons, because those are the ones that have the vast majority of the mass for the atom. And it turns out that for a given element, they all have the same number of protons. That's what distinguishes one element from another. But sometimes atoms of the same element can have different numbers of neutrons in the nucleus and thus have different masses. Okay? So that's what we refer to as isotopes. These are going to be atoms of a certain element that have different numbers of neutrons. So they differ in the number of neutrons, and then as a result have different mass numbers. All right, so Dalton's proposition that all atoms of a given element have the same mass is not true. There are the existence of isotopes, and so just to rub a little bit more salt in the wound, I'll write right here that Dalton was wrong. Okay, about this, he was right about a lot of things, but he was wrong about this. Okay, so Dalton did not. I mean, understandable, they didn't know about neutrons at the time, so no way he could have known this. But basically, sometimes atoms of the same element have different numbers of neutrons and thus have different masses, and those are referred to as isotopes. Okay. Now, isotopes are not terribly important from a chemistry standpoint because the physical and chemical properties for isotopes of a given element are very similar to each other. That doesn't really change things a whole lot. It's important in nuclear chemistry, which we're not going to talk about in this class. So if you're talking about things related to nuclear energy and stuff that you'll learn a little bit about in Chem 2, isotopes have very different properties from that standpoint, but the chemical properties and the physical properties that we care about in this course are going to be the same for all isotopes. So if you have the properties of isotopes for a given element, they're very nearly identical. All right, so there are three naturally occurring isotopes of carbon on planet Earth, and whichever three of those isotopes you look at, their properties in terms of their appearance, their melting point, their density, their chemical reactions they do, all pretty much the same. So the isotopes doesn't really affect things too much in general, at least from a chemistry standpoint. So here's some examples of isotopes. Let's start with the simplest atom on the periodic table, which is hydrogen. So hydrogen has a symbol H, and it has one proton in the nucleus, so we would put Z down there as 1 for hydrogen, indicating that it has one proton in the nucleus. And then one of the isotopes of hydrogen does not have any neutrons at all, which means that its mass number is also 1. It has 1 proton, 0 neutrons, so that means the mass number, which is the sum of the two, is also 1. So this is the most abundant isotope of hydrogen, the one that makes up about, I think it's like 99.9% of hydrogen on Earth is in this form. And it has, as I said, 1 proton and 0 neutrons. Okay? But there are two other forms of hydrogen. One of them is naturally occurring. It's called deuterium, is a synonym for it, but it's also just hydrogen. So the symbol would start out the same. It's still hydrogen. It still has 1 proton in the nucleus because any form of hydrogen should have 1 proton in the nucleus. But this isotope also has 1 neutron. So this has 1 proton, but also has 1 neutron, and thus the mass number is 2. So this is a second isotope of hydrogen. Same number of protons, but different numbers of neutrons. And then the third isotope of hydrogen that's known, is used a lot in biomedical studies, is called tritium, but also it's just another form of hydrogen. It has 1 proton in the nucleus. We still have the same atomic number as we would for for any isotope of hydrogen, but this one now has 2 neutrons in the nucleus, and thus the mass number is 3. So as you can see, there are 3 isotopes of hydrogen.
They all have one proton, but they have different numbers of neutrons, and that's what distinguishes them from each other. So that's sort of the definition of isotope. That's an example of an element that has them. So as a sample problem, let's consider the element palladium. Very, very useful in jewelry, in cars, catalysis. But anyway, let's look at these two naturally occurring isotopes of palladium and determine the number of protons and neutrons. So this is basically one thing you'll have to do on the homework assignment is look at an atomic symbol and answer questions about it, about how many protons, how many neutrons, how many whatever does that have, okay? So the one that's easy to find is the number of protons, because that's going to be given directly by the bottom number there, which we call Z. So that number of protons is going to be equal to 46. This asks for, let's see, protons, electrons, and neutrons. All right, the number of neutrons we can get from the mass number. So the number of neutrons we cannot get directly, but we know that the number of neutrons plus the number of protons is equal to the mass number A. That's going to be this top number here, which means that the number of neutrons plus the number of protons, which is 46, is equal to the mass number, which is 106. And so then with a little bit of simple algebra, solving for number of neutrons, the number of neutrons is going to be 60, okay? So if the mass number is 106, the number of protons is 46, that means there has to be 60 neutrons for those to add up to be 106, okay? So for a number of neutrons, we have to use the mass number, but it's not going to be directly given us. We have to subtract the number of protons. And then finally, what we haven't talked about directly yet, but is fairly simple to do, is we also ask for the number of electrons. And in a neutral element, in an element that does, in a neutral atom, one that doesn't have any charge associated with it, the number of electrons has to equal the number of protons. So as we said, an atom has no net charge associated with it, which means that it has to have equal numbers of protons and electrons. So if this has 46 protons, it must also have 46 electrons because it's a neutral atom, okay? So the only one that required a little bit of effort was the number of neutrons, because we had to use the mass number and do some very simple algebra to get it. Now if we go to another isotope of palladium and ask for the same thing, this is still the same element. It has the same symbol, has the same atomic number 46 as it should, and so the number of protons, the number of electrons has to be the same, okay? It's the same exact element, so it has the same number of protons and the same number of electrons, which are both 46, okay? So any isotope of palladium would have 46 protons, 46 electrons. But the difference is going to be in the number of neutrons, so when we solve for that, in this case, the mass number of this isotope is 108, which means that when we solve for the number of neutrons, we take the mass number and subtract from that the number of protons, which is still 46. And that means this isotope has 62 neutrons. So if you're comparing two isotopes, the only difference should be the number of neutrons, nothing else. Okay, if they're the same element, which they are here, they'll have the same number of protons, same number of electrons, but different numbers of neutrons. All right, any questions on that? Yeah, go, thumbs up. Okay, all right, good. All right, so let's just do one more, just to practice going the other direction, writing the atomic symbol. So if we have a fictitious element with the symbol Q, with 34 protons and 43 neutrons, what is the proper atomic symbol? So recall that the anatomy of an atomic symbol is the element symbol as in the middle, a subscript, which is the atomic number, a superscript, which is the mass number. All right, so again, this Z here, which is the atomic number, is just the number of protons, which we're telling you directly is 34, okay? So that's given to us directly in the problem, but this A here is not just the number of neutrons, remember, this is the number of protons plus the number of neutrons. So to get that part of the atomic symbol, we have to add the two. So we have 34 protons. We're told that we have 43 neutrons, and that means the sum of the two is 77. That's going to be the number we're going to put in the superscript in the A position for mass number. And so the final symbol is going to be Q is the symbol, the atomic number of 34, the mass number of 77, and that's how we would write it. Okay, so typically in Blackboard, this would be a multiple choice question where you have to identify then the correct symbol using these principles. All right, so that I don't think is terribly difficult. Let's move on now to talk a slight extension of this, which is the formation of ions. We will talk, again, ions is something we're going to talk a lot more about later, but for now we want to know the basics of this. And as we already said, neutral atoms, atoms that have no charge associated with them, are going to contain equal numbers of protons and electrons. All right, so that's going to be true for a neutral atom, and that's because we need to balance the charge. We need to have zero charge in total. But it is possible for many elements, and we will again deal with this in about probably starting in chapter 3, it is possible for many elements to form ions, which are basically atoms that have acquired a net positive or a net negative charge, which means they don't have the same numbers of protons and electrons. But when we're forming an ion, all we're going to ever do is remove or add electrons. All right? Forming ions never involves doing anything to the nucleus, because if we change the number of protons, we're going to change the identity of the element altogether. All right, so in all of chemistry, really, I mean, people think chemistry is this really complex science, and to some extent it is, but all of chemistry is basically just moving electrons around, either taking electrons away or giving it more electrons, or exchanging electrons between two elements. That's really what all of chemistry is, and it's all about the electrons. So when we're forming ions, I want to reiterate that we're never going to add or remove protons from the nucleus. Add to or remove protons from the nucleus. Because if you do that, this is going to change the identity of the atom, and we're not doing any chemistry in the nucleus. We're only going to be involving the electrons. All right. So when an atom acquires a positive or negative charge, it's still the same element. It just has either too few or too many electrons, but it's still the same element. It doesn't change the number of protons that it has in the nucleus. And it's pretty simple to do this, because if we want to know how many electrons do we need, we just basically add one electron for each negative charge that the ion has. Or if it's a positively charged ion, we subtract one electron. Okay, so here's some examples of how we do that, just taking what we learned last time one step further. So when you indicate the symbol, the atomic symbol of an ion, the only difference is that now in the top right, we're going to have a number, a positive or negative number, that indicates the charge being either positive or negative. So in a neutral atom, this is not going to be there at all. That indicates that the charge is balanced. But in an ion, you're going to indicate up here in the top right what the charge is. And this is going to ask again how many protons, neutrons, and electrons are there. So the number of protons and the number of neutrons we get in exactly the same way. We look at the atomic number and the mass number, and we get those that way. So the number of protons is going to be 77. IR, the symbol stands for iridium. That's my favorite element in the world, so I'll mention that more than once probably. You might have it in your phone right now, if depending what type of phone you have, but it's my favorite one. So I'll say that again. All right, and then so that's going to be the number of protons. We get that the same way, and then similarly, number of protons and neutrons is still going to be equal to the mass number 192. So the formation of ions doesn't influence anything in the nucleus. So the mass number, atomic number still have the same definition in ions, and that means in this case the number of neutrons is going to be the mass number 192. Subtracting from that the number of protons, and the rest of that mass is then the number of neutrons, 115. And then the number of electrons in this case, though, is going to be different because this is an ion. So we have 77 protons in the nucleus, but this has a 3+ charge, which means that we're going to have 3 fewer electrons than protons, that in net we have a positive charge. So if we have a charge of +3, 77 protons, we have 3 fewer electrons, which means that this +3 ion is going to have 74 electrons, okay? And that's then what gives it the +3 charge, because it has 3 more protons than it has electrons, which means it has 3 extra positive charges for a +3 charge, okay? So that's how we do number of electrons in a positive ion. Negative ion is same concept, just a little bit different because we have now a negative charge associated with this. So number of protons is still the mass number, which is 16. Number of neutrons is still the atomic number, which is 16. Number of neutrons is still the mass number minus the atomic number, which is 17 in this case. So those numbers exactly the same. We just use these two left-hand numbers to get those. But then for the number of electrons in an ion, we start with the number of protons that we have. In this case, we have 2 extra negative charges, which means we have 2 extra electrons, so we're going to add 2 to this. All right, so this sulfur 2- anion has 18 electrons because of the -2 charge. All right, so if it's positive charge, you take away electrons. If it's negative charge, you add electrons. It's as simple as that. All right. All right, and then the last 2 things we'll talk about, if we have time, we do, I think, is in addition to using the atomic symbol, we can also use the periodic table to find the number of protons. So we're going to, as I said, we're going to talk about the periodic table in a great level of detail. It's one of the most enjoyable topics in this course, in all honesty, in my opinion. And we're going to see this later on. But for now, you're always going to have the periodic table on the exam. So if we ask you how many protons are in a certain atom, an atom of a certain element, you can use the periodic table very easily to do that. So I don't think I have, I think I need to get it. Oh, I do have it. No, this is from last semester. This should work. I'm going to open up the periodic table so you can see what ours looks like if you haven't looked at it yet. Maybe. Come on. There it goes. All right, why didn't it open? All right, so here's our periodic table. This is what it looks like. So basically each of these boxes represents an element, and if you zoom in on one of those boxes, what it will look like is shown here. Okay? And if you want to know the number of protons for the atomic number, that's going to be the number that's shown above the atomic symbol. So that number up there is the atomic number, which is the number of protons. All right, so again, you always have the periodic table in front of you, so there should never be a reason why you can't figure out how many protons something has if you can find it in the periodic table. This number down here, just to point it out quickly at this stage, is related to the mass number. So we said that the mass number is the number of protons plus the number of neutrons is always a whole number. The numbers below the symbols in the periodic table are going to be related to that. We'll cover this later on. So it's not exactly equal to the mass number, but it's related. But then another note about the atomic number Z is that usually in atomic symbols, we actually leave it out. So we said that the full atomic symbol includes this as a subscript on the left side, but in many cases, we're going to leave it out of the atomic symbol. The reason being that, as you might have already recognized, the atomic number Z and the atomic symbol, the letter that we put in there, those are kind of redundant because for a given element with a given symbol, it's always going to have the same number of protons. You don't have to really specify what that number is. So what that means is that even though for carbon 12, the full symbol would be this, which includes the atomic number Z there in the bottom left, very often what you'll see, including on homework assignments and exams, so start getting accustomed to this, is you'll just see it written as this, just 12C without the 6 there, okay? Now this symbol does not directly tell you how many protons we have, but because it's carbon, it has to have 6. And so if you're given a symbol like this, as is very often the case, you have to go to the periodic table to figure out how many protons there are, unless you memorize the order of the elements in the periodic table, which I don't recommend. If you've been in chemistry as long as I will, you'll learn that naturally, but we're not going to expect you guys to do that. So anyway, if you get a symbol like this that doesn't indicate the atomic number directly, you then have to go to the periodic table. It's carbon, there's a number 6 above it, that means the atomic number is 6, and so we'll have to get used to this. So this is going to be the more common way of doing it. And that's because the atomic number Z is redundant with the symbol. All right, and I know we're getting restless, but we just have a couple more minutes, so last question here is which 2 plus ion has the same number of electrons as Br minus, bromine minus? So we have to first figure out how many electrons this has. So if we go to the periodic table, we see that Br, if we find it here, is atomic number 35. So that means it has 35 protons. I don't know why my pointer's not working for this, but it's over here. 35 is the atomic number for Br. So it has 35 protons. Because it's negatively charged, it has 36 electrons. So what we're looking for now is the 2 plus ion that has the same number of electrons as that. So we're looking for an unknown 2 plus ion, which has 36 electrons. Now, if the charge of this ion is 2 plus, that means it must have 2 extra protons, and that means this 2 plus ion has 38 protons. And so then to identify what this is, we need to figure out which element has 38 protons in the nucleus. We have to go back to the periodic table. All right? So if we go back to the periodic table, I don't know why my pointer's not working in Adobe. I'll have to figure this out. But anyway, if we go back to the periodic table and find the one that has a 38 above it, that's right there, strontium, atomic number 38, Sr, is the symbol. That has 38 protons. That's what we're looking for. And so Sr2 plus would be the 2 plus cation that also has 36 electrons, okay? And then the last one here, which is a little bit weird because we're talking about nuclear chemistry now, but it's a little bit of a preview of what you'll do in Chem 2, is let's say we have the lead 2 plus ion, lead 207. Now what's helpful here is to also look at what the atomic number is that would go down here. So if we look at that for Pb, Pb is over here, number 82. So again, you have to get used to the periodic table, but you'll find these things faster and faster as we go. Lead Pb is number 82, which means it has 82 protons. So the full symbol for this ion that we're starting with is 82. Okay? And we're going to imagine that it loses 2 protons and 2 neutrons. That's what an alpha particle actually is a little particle that includes 2 protons and 2 neutrons, and that's a form of what we call nuclear decay, which we're not going to talk about in this course, but we have the capabilities of doing this problem now. So if it loses an alpha particle, 2 protons and 2 neutrons, what's the atomic symbol that results? So what we're starting with in lead 2 plus is 82 protons. The atomic number is 82. And the number of neutrons, we have 207 minus 82 is 125. And then the number of electrons is 2 fewer because it's a 2 plus charge. We have 80 electrons. Okay, so this is what we're starting with in lead 2 plus, 207 isotope of that. We're telling you that we're losing 2 protons and 2 neutrons. So whatever our new atom is going to be 2 protons fewer than that, so it's going to have 80. It's going to have 2 neutrons fewer than that, so it's going to have 123. And we didn't say anything about the number of electrons, so we'll assume that it has 80 electrons still. Okay? So it's just losing 2 protons, losing 2 neutrons. And now what we have to do is use this information to write the new atomic symbol. All right, so we need to figure out from the periodic table which element has 80 protons. So the one that has the 80 above it is mercury, Hg. Okay, that symbol you don't need to know off the top of your head, but it is mercury, and it has the symbol Hg. And then the new mass number, which is going to be the sum of these two here, is going to be 80 plus 123, which is 203. It has 80 protons and 80 electrons, so there's no net charge, and that means the only thing we have to put in the symbol is the mass number 203. So when this lead 2 plus cation loses 2 protons and 2 neutrons, it forms a neutral mercury atom. Okay, so that's something. Yeah, question? An ion and an isotope in the same molecule. I suppose, but the types of compounds we're going to talk about are either going to have neutral atoms or ions, not both usually. So for this course, one or the other.